Hello, this is Mark Unkefer, and I'm director of the Fiber Optic Sensing Association, and welcome to our October webinar, part of our regular series to promote fiber optic technologies, various use cases. And this month, we're very pleased to have two people from Oz Optics, which has been one of our more active members. Their presentation is on gas-cooled generator applications for fiber optic distributed strain and temperature sensors. So we're going to get exposure to a little bit different use case for us. We have as our presenter Gordon Ewell, who is the Vice President of Test Equipment at Oz, and Garland Best, who is Vice President of Engineering and Components. And I should probably add, Oz is one of the companies that makes us international. They're based in Ottawa, Canada. So Gordon, Garland, we look forward to your presentation.
Oh, thank you very much, Mark. Thank you as well. Yes. I'm Gordon Ewell. As Mark indicated, I'm the Vice President of Test Equipment here at Oz Optics, and I'm with my colleague Garland Best, who is the Vice President of Optical Components.
Nice to be with you all today.
We're delighted to be able to give this presentation on gas-cooled generator applications of distributed fiber optic sensing. The purpose of this webinar is to cover some recent work that was done using some fiber optic sensing in an application involving gas generators. The question came up: can a distributed fiber optic sensor be used to monitor the temperature distribution inside an operating electric generator? Now, this is certainly very important for those people who are in the industry and who want to know, well, are their generators overheating? Are things getting hot? Generally, excessive heat is not a good thing, so you like to keep things at a reasonable operating temperature. Hotspots within the stator core of a generator can lead to catastrophic failure. As you can imagine, things get hot, that's bad. You often get things breaking down because of heat. Things expand unevenly, and you can get short circuits if things start to degrade. Inside an electric generator, there are generally thousands of steel plates that are laminated together within the core. Now, within the core, these laminated plates have insulation surrounding them, and that insulation normally degrades over time. So it's important that this be monitored, because if it degrades too far or too much, then you get catastrophic failure. When you get degradation of this insulation, you get connections between these laminated plates, and that can cause large eddy currents to flow. Now, eddy currents are caused by electromagnetic fields, and of course, in an electric generator, you have very large electric fields at all the time. So you get lots of large eddy currents, which result in heat, because these eddy currents eventually dissipate, and they dissipate by generating heat. Now, as long as these are very localized and very small, they're not a problem. But if they become large, and that can happen when you get multiple laminated plates connecting together because of insulation breakdown, these large eddy currents generate a lot of heat, and that can really cause problems, because if you have enough heat, it will break down the insulation around the wires that are inside your generator. And once you break down the insulation inside the wires or surrounding the wires, then of course your conductors start to short circuit, and that's a really bad thing. So you really like to avoid that. So the whole purpose of this experiment was really to determine, can we monitor what's going on inside the generator while it's running? Now, traditionally, devices called RTDs, which are resistive temperature detectors, they have been used for detecting the hotspots. But unfortunately, each of these requires a separate wire. And so if you have dozens or even hundreds of these RTDs inside a system, that's an awful lot of wiring that you have to deal with. So that can be a big problem. So it's really difficult to use RTDs in a really meaningful way. You can only get limited point coverage. That is, these are detecting the temperature at specific points inside the generator. And you want to have a bigger picture, a broader picture. You know, what's going on between these RTDs? And RTDs alone just won't answer that question. Whereas the beauty of having distributed fiber optic sensing is that it does give you a distributed temperature profile. So you can see what's happening basically anywhere along the length of the fiber. Now, another advantage of using fiber optic sensing is that you avoid the problems associated with strong electromagnetic fields. These electromagnetic fields, which of course exist within these generators, make it difficult to use conventional RTDs or other electronic devices, simply because they introduce a lot of noise, and it makes it hard to make accurate, repeatable measurements. So when you use fiber optic sensing, you get around that problem because they are immune to these electromagnetic fields. So this means that fiber optic sensing is nearly an ideal method for making this sort of temperature measurement, where you want to have a complete picture of what's going on inside the generator. You're no longer limited to specific points. You get the temperature along the entire length of the fiber. Now, I'll point out that unlike a lot of fiber optic applications that use distributed sensing, whether it's strain sensing or temperature sensing or acoustic sensing, what we're dealing with here is really a relatively small volume. That is, we're looking only inside a generator. Most fiber optic distributed sensing applications are used for monitoring long assets such as pipelines or overhead power cables, large structures such as bridges or roadways, things of that nature. So this is a somewhat different type of application where we are looking at something which is limited in size, but it is very difficult to monitor by using other means. Now, the beauty of fiber optic sensing is that the fiber itself is the sensor. So unlike other applications where you have sensors that are either small packages that monitor things in a very limited space, the whole length of the sensor, well, basically is the whole length of the fiber. All of the control circuitry, that is, it does need some control circuitry at some point, that is contained within a device called an interrogator, which is connected to at least one end of the fiber. So it injects signals into the fiber, and it looks at a return signal. And based on the signal processing that is done, we can look and see what the temperature is at any point along that fiber. The interrogator can actually be some distance from the actual generator. Typically, it could be tens or even hundreds of meters. So it does not have to be sitting right beside the generator. It is simply connected to the generator by a lead-in fiber, and then you have the sensing fiber, which is installed inside the generator. Fiber optic sensing itself can be used for measuring temperature or strain over distances as short as a few centimeters up to distances as long as 100 kilometers, or under special circumstances, even longer than that. So in summary, the advantages of the fiber optic sensors, they are electrically insulating. That is, there are no electrical cables required. They're suitable for use in high voltage environments. They are chemically passive. That is, the fiber is basically glass. So the only thing you really have to worry about is the cable, which is the surrounding jacket on the fiber. And that can be made with any one of a number of different types of material to suit the application. And these sensors are immune to electromagnetic interference, and they also operate over a very wide temperature range. So as long as your fiber or your cable is not going to either melt or burst into flame, you're pretty well unlimited in terms of the operating temperature. It can go down to very close to absolute zero at the low end, or as high as a few hundred degrees centigrade. Now, in this particular application, we're looking at temperatures that are typically within the range of anywhere from room temperature up to, well, less than 100 degrees typically. So it's well within the range of what can be handled with a fiber optic distributed sensor.
Okay. At this point, I'd like to talk about the theory that goes into the actual Brillouin sensing system. As this is the system that we've used here uses a function called Brillouin scattering, and it's an interaction between the light that we're going to launch down through the fiber and the fiber material itself, the silicon dioxide, which is sort of a quasi-crystal. You have silicon and oxygen atoms and some germanium atoms to form a lattice. And as the light travels down through the fiber, every now and then a photon of light will actually contact these atoms, and it'll strike and it will set up vibrations within the glass itself. And that vibration depends on the glass material. There are natural resonating frequencies that the glass will want to vibrate at. And so when this hits, the photon will hit and it will get scattered backwards, and it will lose some energy to the glass as a vibration. And as a result, its frequency changes by this amount of vibration energy that it transfers to the glass. And this change in the frequency due to the loss of energy is what's known as the Brillouin shift. Now, this depends solely on the glass material itself, but also upon the temperature that the fiber is at, and whether or not the fiber is under some sort of strain or tension. You can imagine, the analogy I like to make is a guitar string. A guitar string, when you pluck on it, it has a natural frequency. So when you pluck on it, you get a certain tone. Now you can change that tone by tightening the guitar key, which increases the tension on the wire, so now it vibrates at a higher frequency. Similarly, if you apply some heat to the guitar wire, it will tend to expand and soften a bit, and that also changes the frequency. So temperature and strain changes the natural vibration frequency of matter. And by using the light to probe this natural vibration frequency, we can measure the temperature and strain along the fiber. And if we do this right, we can actually measure it along the entire length of the fiber and know it not just the change in the frequency of temperature and strain, but also in terms of position. This picture here gives a basic layout of how a Brillouin sensor works. It's fairly simplified, but it gives you the essentials of it. We start off with a highly stable laser over on the left, and it is modulated by a pulse modulator. And from this, we're able to make very small pulses and send them down through the fiber one at a time. So it's a sharp pulse that we just send off, and as it travels through the fiber, what we're looking for is the echo as the light gets reflected back. A circulator allows us to send the light out in one direction through the sensing fiber, and then when the light comes back, it sends it down to an optical receiver, where we are able to do the analysis of the frequency, intensity versus time. Now, in our picture here, we're showing a fiber, and there's one section where there's a hot spot, or an area that's under strain. Now, in that section, because of this strain or change in temperature, the natural vibration frequency is different. So the light, as it goes in through the fiber and reflects back, parts that are reflected from the beginning of the fiber will have one frequency, part that hits the middle of the fiber where the air temperatures change, will come back at another frequency, and afterwards, when it comes back again to a part of the fiber that's not altered, it gets reflected back again at this original Brillouin frequency shift. So we send this pulse back, and we're looking at the echo, and we're watching the frequency change of the echo over time, and from this we can figure out along the fiber where we have a change in either strain or temperature. Now, to assist us, there's a couple of different configurations. We can actually improve our signal strength by adding an additional pump laser on the opposite of the fiber going in the opposite direction. This actually acts as an amplifier to amplify the signals that we're dealing with, because we're actually measuring a very weak signal. It is, we are actually getting reflections coming back that are on the order of nanowatts to picowatts of energy. The pump laser that we use acts as an amplifier so that we can actually get more signal back. And with the increased signal, we're able to actually achieve better resolution and precision. So without getting in too much math, we can talk about the way that we can analyze the change in the Brillouin frequency, which we call the Brillouin frequency is known as mu b. Okay, it is a function of temperature and time, and the functions are linear. So if we were trying to measure strain while keeping temperature constant, then we would start off with an initial change in frequency at a certain fixed strain and temperature, okay, which is known as mu b naught as a function of temperature and strain. And then you have a strain coefficient. So the change in strain multiplied by the coefficient will tell you the change in the Brillouin frequency. Similarly, in our second equation, where we look at it as a change in the Brillouin frequency versus temperature, we have initial Brillouin frequency, which represents static, room temperature, no strain environment, and then a change, which is this coefficient CT, and the change versus the original temperature over the time. So we have two independent equations here to describe how the frequency changes over temperature and time. Okay, and they're both straightforward linear equations. By using these equations during our analysis, we're able to calculate the change in the Brillouin frequency as you change the temperature in the strain. So as I said initially, what we're doing is we're sending a small short pulse through the fiber, and we're monitoring the echo as it comes back. And what we're doing is we're measuring the time it takes for the echo to go through the fiber. So by injecting this pulse of light into the fiber, the time that the return signal relative to the generation of pulse gives us the location. It's basically you just measure the time and you multiply that by the speed of light divided by the refractive index of the glass, because the glass will slow it down relative to the speed of light in a vacuum. These are known parameters for the fiber. So once you know the speed of light in a fiber, you just measure the time in nanoseconds, and you're able to calculate the distance along the fiber in terms of meters. So it's just a straight measure of speed of light and measure the time. This would be an example of what we would get out in terms of a Brillouin spectrum. Okay, and what this is actually measuring is the actual change in the frequency of a reflected beam compared to the initial light that we sent out through the fiber. That's what we do in order to measure the Brillouin shift. We measure the frequency change compared to the original light that we sent out through the fiber. So in this case, we've taken a spectrum that's roughly 4,600 meters along a fiber, and we have a frequency shift, and the frequency shift is roughly 10,850 megahertz. Okay, so these are the sort of frequencies we're looking at. What we do in our lab is we actually have an experimental setup where we are able to apply temperature and strain onto a fiber and measure these frequencies and establish these coefficients. These are calibrated and recorded into our interrogator, and it's used to actually measure temperature and strain based on the location of this peak Brillouin frequency along the fiber. Now, one of the questions that would come up is, how do you tell the difference between strain-induced changes and temperature-induced changes? Because Brillouin frequency changes can be affected by both. So if you have both strain and temperature acting on a fiber, the trick is, how do you know which is causing it? Is it a change in the strain, or is it a change in the temperature? So the trick to that is how we cable the fiber and install it into our location. Okay? We want to be able to come up with a way that we can isolate the fiber either from strain or from temperature, so that we can confirm that only one of those features are acting on the fiber, not both of them. So normally, in the case that we're doing here, where we're doing a gas-cooled generator, and we're concerned primarily with changes in temperature, what we do is we actually will be installing the fiber inside a hollow tube so that the fiber can move freely inside the hollow tube. It can only move by like a millimeter or so in either direction, okay? But it's enough to ensure that there's no excess strain on the fiber in any given location. Now, if we wanted to measure both strain and temperature in a scenario, then what we can do is we can lay two fibers side by side. One which is in the tubing, which isolates it from strain, and the other one which is bonded directly onto the material that we're measuring the strain off. Okay, and as long as they're side by side close enough together that they're measuring the same temperature and they're influenced with the same temperature, then we have one fiber that's affected by temperature alone and another fiber that's affected by strain and temperature. And so by analyzing two Brillouin spectrum at the same location, we can actually distinguish between the strain effect and the temperature effect and measure both simultaneously. So that's the critical point in order to do this. We have to make sure that for measuring temperature alone, we keep the fiber in influence where it's not affected by strain. Now, there's actually two different ways that you can actually do measurements of Brillouin spectrum. There's one system which is known as a Brillouin optical time domain reflectometer, or BOTDR, and another method called Brillouin Optical Time Domain Analyzer, or BOTDA. The key difference between these two is whether or not we have a pump laser at the far end of the fiber to act as an amplifier. So a BOTDR, which is a reflectometer system, has no pump. It just sends a pulse down and it measures an echo. Okay, so one advantage of that system is that you only need access to one end of the fiber. The other end of the fiber can go off into your instrument in somewhere, say, 1 kilometer away or 5 kilometers away, and you don't have to worry about it. Okay, light goes in to one end. You don't have to worry about the light on the other side. You're just looking for these weak echoes that are coming back along the fiber. Now, the drawback of that system is that these signals are very weak. And because they are weak, you have to do a lot of measurements repeatedly over and over and over again in order to extract out the useful information from any sort of background signal or light that's coming through. So it generally takes longer to make a measurement. The range is not as necessarily as far as what you can get with a BOTDA system. Okay, and you don't necessarily get the same degree of resolution because of the weakness of the interaction. Now, with a BOTDA system, where we have the continuous pump going into the far end of the fiber, this actually acts as an amplifier. It amplifies the signal coming back. And by doing so, we're able to get a much stronger signal coming back over, for a given length of fiber and a given length of pulse conditions. It allows us to extract useful information over longer ranges. It allows us to extract useful information using a much shorter pulse length, which increases our resolution of our instrument, because the shorter the pulses that we send down, the higher spatial resolution we can measure along the fiber, because there's a smaller range of time. As we know with that first equation, the distance you measure is determined by the time it takes for the pulse to be reflected back, and that time resolution depends on the time resolution of your pulses. So shorter pulses give you higher resolution. Okay, so with a BOTDA system where we have the amplifier, you get longer range, you get higher resolution, you get greater sensitivity. The drawback is that you have to have access to both ends of the fiber. Typically, you need to have a loop-back system where the fiber comes back, goes out from your interrogator, goes through your system, and then has to come back to your interrogator, because all your instruments are at that location. Your both of these lasers, the probe laser and the pump laser, and your interrogator, which is doing the frequency analysis. So if you have to have access, if you can have access to both ends of the fiber, then the BOTDA system is advantageous. But if you can only access one end of the fiber and the far end is somewhere way out there that you can't access, then a BOTDR becomes your critical solution.
Okay, thank you very much, Garland, for that explanation. Now, getting back to the actual implementation in a gas-fired or gas-cooled generator, here we have basically a schematic or a drawing of a gas-cooled generator. You can see that the actual generator itself is a big complex device in the middle, but you can see that there is airflow around that device. The blue lines indicate cool air coming in, and the red lines indicate the hot air being extracted. Now what we have here is a picture actually showing the installation of the fiber installed on what is called the stator wedges. Now, for those who are unfamiliar with the terminology, a stator wedge is basically the region in between those bumps. You can see ridges running along the inside of the generator, and the wedge is really the area between those bumps. And all that is really required is that the fiber be somehow glued in place all along those valleys. So the white material you see is the epoxy, which is holding the fiber in place. And because of those valleys, they're basically out of the way of the moving parts of the generator. This is a picture showing a slightly different configuration. This is a hydrogen-cooled generator. And in this particular application, the fiber was installed slightly differently. It's actually underneath the stator wedges rather than being on top of the stator wedges. The difference is that when the fiber is installed on top of the stator wedges, basically on one side it has the volume of the enclosure there, and on the other side it is exposed to air. Whereas in the case where the fiber is installed under the stator, that means that it's not exposed to air on one side. It's sort of partially buried, if you'd like, inside the windings. Or certainly it's much deeper into the instrument, so it's not exposed to the air directly. here you can see a close-up. And right in the center of the picture, you can see a couple of fibers, just a short length there. At that point, they are exposed, but they then disappear out of sight where they go underneath the stator wedges. So basically, you can think of the stator wedge as something which, in this case, is actually covering up the fiber. Now, this is now showing the measurements that were taken along the length of the fiber under different operating conditions. That is, the four wavy lines that you see in the graph show the generator generating different levels of power, with the red line corresponding to the temperature distribution at the low power generating condition. And as we move up through the blue line, the green line, and the cyan line, we have higher power generation taking place. That, of course, means higher operating temperature. So we immediately see that as the temperature, or as more power is being generated, as we would expect, the inner workings of the generator are getting warmer. What we also see here, because of the waviness, that's actually corresponding to the airflow that's flowing into and around the different parts of the stator. Where we have the lowest temperatures, that would be where cool air is flowing into the generator, and where we have the hotter temperatures, that would correspond to areas that are more, farther away from the cool air. So as the air heats up, you get the higher temperatures. Now, as you can see along the bottom part of that, we have a distance scale. And we're talking only a few meters here. So it's not a large distance we're talking about here. It's only a few meters from the beginning of that graph to the end. And as you'd expect, a generator is not all that large. It's only a few meters long. So even though we're using distributed fiber optic sensing, we're using it over a very short distance, or relatively short distance. The temperatures you can see on the vertical scale range from about 25 degrees up to about 42 degrees. Here's a slightly different graph showing similar information with a picture of the generator sort of superimposed on that. But again, the key point here is that the cooler temperatures correspond to the cool air coming into the generator, and the higher points, or the peaks in the graph, correspond to the air after it's been heated up. So here are some actual measurements that were taken. You can see the load on the generator in the left-hand column. That's how much power the generator was generating. You see some temperature readings showing the temperature of the cold air as it enters, the hot air as it exits, some temperatures showing the embedded RTDs. So in this case, we were comparing the temperatures to RTDs. And there's an average trough temperature and average peak. But we're comparing that to the DSTS that was measuring the temperature. So really the important thing here is to look at the Oz DSTS measurements compared to the embedded measurements. Now, there is a little bit of a discrepancy. For example, you can see 78 degrees for the embedded temperature, and the Oz temperature was 68 degrees. If you move down to a lower power generating rate of 64 degrees, well, that corresponds fairly closely with the DSTS measurement of 62 degrees. And if you move down to the lowest generating power of 45 degrees, we have a measured temperature using the DSTS of 53 degrees. Now, there is an explanation as to why these are somewhat different. Because the RTDs themselves were somewhat more protected from the airflow, it is expected that the actual temperature that they would measure would be higher, whereas the distributed sensing fiber was more exposed to the airflow. It would show a slightly lower temperature. That's certainly what we are seeing in the highest readings there, the first line. In the lowest line, where we have the 26 megavolt amp power being generated, we can see that the Oz DSTS is measuring a higher temperature than what the RTDs measured. And it is believed that in this case, since the measurements were made shortly after the generator was powered up, we think that the whole system had not yet thermally stabilized. That is, the temperature that the fiber was measuring was where it was hotter, whereas the RTD, being a little bit further into the mass, the thermal mass of the generator, it took a little bit longer to heat up. So we suspect that if we had waited a while until a thermal stabilization had taken place, we would have seen better agreement for that. So those were the initial tests that were done. Now, one of the things that people wanted to know was what sort of spatial resolution could be achieved with this unit. That is, if you have a very localized hotspot, which might only be on the order of a centimeter or so, is it going to be able to detect that? So we set up an experiment which basically had a 1 centimeter block of aluminum, and that was heated by a heat source. In this graph, you can see the results. That is, on the vertical scale, we are looking at temperature change. On the horizontal scale is the distance along the length of the fiber. Now, for most of that length, you're seeing basically a lot of noise, but there is a spike about a quarter of the way along the length of that fiber, which really stands out. So that is being generated by this 1 centimeter long hotspot.
Okay. If I may interject here a little bit on this, one of the points we'd like to make here, what we're doing at this point is detecting hotspots as opposed to actively measuring the temperature of a hotspot. Here the spot is quite small. It's about 1 centimeter in length. And if you look up our specifications for our Brillouin sensor, the shortest pulse lengths we're measuring, we say that our measurement resolution is 10 centimeters. So what this is telling us is that somewhere within within a range of about 10 centimeters at this distance, there is a hot spot and it's elevating the temperature. Now, whether it's actually at 62 or 72 degrees is subject to interpretation because the temperature is being somewhat average. But the critical point here is to indicate that we can actually detect a hot spot, even though it's a much finer distance than the actual spatial resolution being used to make the measurement here.
Very good point, Carolyn. Thank you. Here we have a blow-up of that result where you can clearly see that there is a peak there. So obviously something's going on there, and under actual operating conditions, this would alert an operator to look further to see what might be causing that hotspot to occur. Here we have another graph, again showing the temperatures that are measured along the length of the fiber, again under different power generating conditions. Now in this case, the point right in the middle of the graph is actually what we would call the loopback point. So that's the far end of the fiber before the fiber comes back. Recall that the fiber goes from the interrogator through the generator, and then it is looped back through the generator again. So that point right in the middle corresponds to the loopback point. And as we would expect, the graph is roughly symmetrical about that point, which indicates that the fiber, both going out and coming back, are experiencing similar temperature changes.
One point I'd like to make, in these experiments that you're seeing here, we have the fiber going in and out along one single stator within the electrical generator. this experiment was to show the practicality of being able to make the measurement. Now, the long-term goal in an actual setup, we will actually have the fiber run back and forth many times, and each one will go along a different stator within the generator. So even though here we've only gone a few meters, in a real-world application, we'll be going back and forth hundreds of times as we go along each stator. And so by looking at the graphs here, you would see within the first section the behavior of one stator coil, the next section, the next stator coil, the next distance along the next stator coil, and so forth. So with this method, we can use one fiber to monitor all the stator coils within the generator, and not just a single stator coil is what we've done here in our experiment.
Good point, Garland. Now here we have some actual test results showing the actual numbers that were measured. Now again, it's under different power levels. The important thing here is to look at the last two columns where you have the temperature from the embedded RTD and the temperature measured by the DSTS. Now here, since the fiber was located underneath the stator wedges, that meant that it was protected from direct airflow. And in that case, you see very good agreement between the RTD measurements and the DSTS measurements. It's generally, at most, the difference is about a degree or slightly more, but very good agreement. You've got almost 55 degrees and 55.8, 58.5 versus 60.2, and so on. So as long as that fiber is protected from direct airflow, you get very good agreement between the DSTS measurements and the embedded RTD measurements. So from this, basically, we've reached the conclusion that, yes, DSTS is able to provide a distributed temperature measurement within the stator of an electric generator. That's very useful for those that are involved in operating or maintaining power generators. And we're certainly expecting a lot of interest in this sort of application. And also, as pointed out, the measurements show excellent agreement with the point sensors. So with that, we'd certainly like to acknowledge those companies that helped us with these measurements, as we couldn't have done it on our own, Calpine Corporation and QPS Photronics, Inc. So we'd like to thank you very much for watching this webinar. If you would like any further information, you can certainly visit our website, where we have a wealth of videos and other presentations that provide additional information on DSTS sensors. Are there any questions?
We do, and let me just start. This is Mark again, and just kind of what sort of fiber do you need as a sensing fiber, and do you need any particular kind of special optical fiber for the application, or can you use all of them?
For the application, one of the advantages of the Brillouin sensor is it works with perfectly ordinary telecom-based fiber. So the same stuff is being laid out from hundreds of kilometers, thousands of kilometers throughout the world. We're using that fiber, single-mode fiber, for telecommunications applications in order to use it as a detector, which means that the material is widely available and relatively inexpensive. Now, ordinary telecom fiber does have a standard coating, which is meant for relatively benign conditions. In our application here, we were looking at temperatures up to about 100 degrees Celsius, so we could use standard fiber with standard coating, which has an acrylate. Now, if the end use is for a higher temperature, say 200 degrees or more, then what you had to pay attention to is the coating. You had to pick something. One option would be something called polyamide coating, which can safely handle up to about 200 degrees Celsius. If you feel that you're going to be in an environment that hits higher than that, then we have to use even more specialized coatings onto the fiber, either, say, a metal coating or a carbon coating, which will protect the fiber even at these very high temperatures. So in the application we've done here, it's perfectly normal fiber, but if we had to go up to higher temperatures, what we had to pay attention to is really not the fiber itself, but the coating on the fiber. Does that answer your question?
That does. Thank you very much. One of the issues is another question, sort of related question, is since you can make measurements on fibers in a very limited range of a few centimeters, and you can also make measurements of up to 100 kilometers in length. Can you get the same resolution on the entire length of a long fiber?
Well, the short answer to that is no. The signal strength is related to the energy within the optical pulse. So in very long fibers, the optical signals will be attenuated to a point where the signal is basically overwhelmed by noise. This means that longer pulses are required in order to receive an acceptable signal. With longer pulses, the spatial resolution is reduced. So that means that if you have a fiber that is 100 kilometers long, the optical pulses might have to be a couple of hundred nanoseconds in duration. This corresponds to a fiber, a pulse length on the order of about 20 meters or so. So with long pulses, you cannot achieve the same resolution that you would achieve when you're using short fibers and short pulses, which could be on the order of 1 nanosecond long. So there is definitely a trade-off between the fiber length and the spatial resolution.
Now, that being said, it should be noted that we can get these fine resolution of like 10 centimeters, even over distances of more than a kilometer. In fact, I think we can achieve it to about 4 or 5 kilometers at the highest resolution.
Okay, that's very helpful. Actually, I had a couple questions about the interrogators. If you want to monitor multiple generators, is a separate interrogator required for each one? And sort of related question is the interrogator that we're using here in this use case the same that you would use for pipelines or for power cables?
I'll answer that second question first. Yes, the same interrogator would be used for different applications. So it's not a unique application. There might be some fine-tuning required for different applications, but generally it's the same basic interrogator, whether you're looking at a generator or monitoring a pipeline or monitoring an overhead power cable or any other application. It's basically the same instrument. Now, to answer the first part of the question, okay, you can put multiple fibers in series if you want. So if you wanted to monitor different devices or different generators all at the same time, you can do so. You just have to wire them or put the fibers in series. As long as the total length is still less than something on the order of a kilometer or so, there should be no problem. However, you do have to watch out for certain things. That is, when you have multiple fibers in series, you have to do a baseline. And the baseline that you get for one fiber might not be the same as the baseline you would get for another fiber. The easiest thing to do is just to wire them in series and do a baseline measurement, because the Brillouin sensor basically measures changes. So once you make your baseline measurement, any changes, and it doesn't matter which generator you're monitoring, it will be able to measure these changes. Now, there is another way of doing it. You can use an optical switch. Now, if you have an optical switch, that gives you perhaps a little bit more flexibility. So you still have one interrogator with an optical switch, which would select any one of the generators that you want to monitor. Now, it means then that you're only monitoring one generator at a time, but basically the interrogator can give it its full attention during that time period. And you can switch fairly quickly from one switch to another.
So you can imagine in that sort of scenario, let's say that you had a dozen of these generators within a power plant. you could use a fiber optic switch system, and you could just go sequentially from one generator to the next. So the switch would go to fiber loop number 1, and you'd be measuring the temperature effects of generator number 1. Then it switches over to fiber number 2, and you measure the temperature changes in fiber number 2. So as long as we do this on a regular basis, and the time scale between monitoring from one channel to the next is on the order of about a minute, you can go through all of them fairly quickly and regularly and catch any sort of issues that may occur within a relatively short time scale. So a fiber optic switch is one option that allows you to work on multiple stations together. And we do have a version of the interrogator that operates automatically with these multiple channel switches, which will allow you to monitor multiple stations at a time.
Let me just kind of drill down a little bit on those last answers. Can I make my baseline measurements with the fiber on a spool before it's installed, before installing the fiber in a system?
That would generally cause problems. The reason is that when you have the fiber on a spool, it is going to be under a certain amount of strain. So even if you know the temperature accurately, as soon as you take that fiber off the spool and install it in some other application, you're changing the strain. So right off the bat, you're going to be shifting your Brillouin frequency.
So the better solution is you install the fiber, and before the generator is actually turned on, you actually get a recording of the general environment of the generator, noting the ambient temperature inside at a few locations, and that gives you your initial reference point of what the actual temperature is from the generator. And so you have your baseline gathering at that point, and you have your baseline temperature to go against, and then you operate the turbine, and you're noticing the change in temperature from that initial ambient condition that you started the measurements with. And from that way, you get everything calibrated and everything is giving you accurate measurements.
That's good, thank you. And I think that ends the questions that we've had so far. So I'll thank you both for a very informative presentation. I will ask one question answer one question that usually comes up. We will have this webinar posted on the FOSA website, but also on our YouTube page fairly quickly, probably in another day or so. So anyone who wants to can go back over and take a look at that again. Also, just to provide a couple of updating information about some upcoming events. In November, we will be having a presentation from CFOM. We'll be having a update on some of the work that they have been doing in fiber optic sensing, and it will be by Chris Baldwin, who's the Strategic Technology Manager at Weatherford. That will be on November 15th, on Thursday, and also at this particular time. And in December, in the December 5th and 6th, FOSA will be having its annual membership meeting. It'll be in Washington, D.C., and we now have registration links for that. And also in December, we will be having another webinar with a new member, Smart Pipe Technologies, and that will be on December 20th, again at 11 a.m. Eastern Time. Those are both available on, information is available on the website. So Garland, Gordon, thank you very much for what was a very informative presentation.
You're very welcome.
Thank you very much.
And that concludes our webinar.